All right, well, today we're going to continue talking about a torque-free motion of a rigid body. And we're going to just dive in. So last time we ended talking about torque-free motion of a rigid body where all of the principal moments of inertia were different. And we also made an approximation that we were mostly spinning about one direction. We're going to drop that assumption that we're mostly spinning around one direction, but we'll make this other assumption that two of the moments of inertia are equal. And that's what we mean by symmetric. So, and I think I said this in a previous lecture here, symmetric, put it in quotes, it just means that two principal moments of inertia are equal. So it could be something that geometrically looks symmetric, like a tube. I've got some kind of tube thing here. Or it could be a box or something that just happens to have a shape where if you calculate the moments of inertia, two of them are equal. So it could be a box, I don't know, something like this, square box, or rectangular looking thing. As long as you got two moments of inertia equal. So we would say the moment of inertia, this one's I3, about the third direction, and it's not equal to I1. Here's I1. But here, about the B2 direction, that moment of inertia is also I1. And same thing here, I3, not equal to I1. We haven't yet decided whether, or figured out if I3 is greater than I1. I guess you could figure out from how these things were drawn. But so you could have things that are kind of tall and are symmetric, and I just got some kind of plate. It's kind of, oh, you can kind of see it's got green in it, so it picks up the green screen. This is a plate, so it's flat-ish. Kind of a Spanish design. This is Valencia, Spain behind me. Nice place on the Mediterranean coast. So we go back to what are Euler's equations for a free rigid body written in a principal axis frame. And I've written it a few times now. So that's the first ODE. This is giving the time rates of change of the components of the angular velocity as seen in the body fixed frame. That's what omega 1, omega 2, and omega 3 are. And here's this one, I3 omega 3 dot minus I1 minus I2 omega 3, no, omega 1 omega 2. So if we have, we're making the assumption here, right, that I2 is equal to I1. That's what defines a symmetric rigid body. Two of them are equal. We're choosing I1 and I2 to be equal and I3 to be the odd one out. So that would mean that over here, this term is exactly 0. So that means omega 3 dot equals 0, which means omega 3 is a constant in time. So we could do something similar to what we did last time where, okay, this here, omega 3 is constant. This thing becomes, we'll use I1 So we've got I1 minus I3 and I3 minus I1. So those are just the reverse of each other. Using the same approach as last time, right? We called that omega S. So we just sort of labeled that as omega 3. That's the constant. It's constant during motion. And then we defined omega n squared, just like last time, but now with I1 equal to I2, this looks even simpler. So this is I1 minus I3 squared over I1 squared times omega s squared. So if we define that, then from these other two rigid body equations of motion, we get something that looks very similar to last time. It's just that it's now exact because we've made this assumption of a symmetric rigid body. Well, what does it matter that it's exact? It means that this holds not just for small deviations from the axis about which we're spinning. This will hold for any deviation. So we have this essentially using the same procedure as last time, but now it's exact. So now the equations are exact, not approximate. The differential equations. We're going to use some other notation that follows what the book uses. So if you do want to follow along, this is at the end of each chapter, they have these things called tutorials. So this is tutorial 11.1, and that's on page 515, and that's where I'm getting my things. I'm going to follow the notation that's used there. So there they let I1 and I2, they call that I naught. And then for the other one, I3, they call that J. So I'll use that same notation. And all that we need to know now is that J is not equal to I naught. There'll be two cases later. Is J greater than I naught, or is J less than I naught? Okay. So we've got a rigid body, and it doesn't necessarily have to look symmetric, right? You could have some weird shape. Here's a GoPro. I don't know what the moments of inertia are, but suppose they're not all equal. Well, I could start shaving off mass in different directions, and I could make two of these moments of inertia equal, and it will not be a symmetric looking shape. But it'll still follow these equations of motion. So, okay, here's our general looking body. We're looking at free rigid body motion, which means the only kind of obvious reference point is the center of mass, G. And we've got two directions where the moment of inertia, two principal axis directions where the moment of inertia is I naught, and some the third direction where it's J. And we're looking at what is the evolution of the angular momentum. This is I, the angular momentum vector of the body fixed frame with respect to the I frame. And the components there, omega 1, omega 2, and omega 3. And so we're looking at the evolution of those things. We've already found that omega 3 is equal to a constant. Now we're solving for omega 1 and omega 2. But we know how to solve this ODE. It's just simple harmonic motion. And omega n, you could tell from here, omega n is always greater than, omega n squared is always greater than 0. So we don't have any unstable motion. Oops. We'll assume some initial conditions. So we'll say at time t equals 0, omega 1 is negative omega naught, and omega 2 is 0. And of course, omega 3 is just, we'll call that omega s. And that's what it will be for all time. So assuming those initial conditions and using these starred equations up here, the solution is omega 1 is negative omega naught cosine omega n t. Omega 2 as a function of time is omega naught sine omega n t. So now we know what omega, the vector, is, in the body fixed frame. It is this. So we've got a part that varies sinusoidally, and then we've got that third component, which is constant. All right. Now, to kind of get the idea of, well, okay, what does this mean? Let me get a rigid body. Here's a rigid body. Rigid body. And then let's say this was the angular momentum vector. So as seen in the rigid body frame, that third component, this is the third component, will be constant. And then the tip will just be going around in a circle with a period of 2 pi over omega n. But that's seen in the body fixed frame. We want to know, how is this thing actually tumbling and moving in space? So one procedure to do that, or at least to get an idea, is to look at the angular momentum. So what's the angular momentum? Here's angular momentum. The angular momentum of the body about the center of mass is what? Well, first we have to write what is the moment of inertia matrix. Well, we've chosen a principal axis frame, so that means we know what this is. We've got I naught at 2 places along the diagonal, and then J, and everything else is zeros. So if we were to write what is the angular momentum, this is in the body fixed frame. This is IG, the body fixed frame, times omega, written in the body fixed frame. You do that matrix multiplication, and you'll get, this is negative I naught, omega naught, cosine, omega nt, I naught, omega naught, sine, omega nt, and j, omega s. And let me draw a sketch. Looking in the B1, B3 plane. Oh, check this out. Look, I've got a blue frame. So what is this? This is B1, B2, B3. So we're looking at, we'll be looking in the B3, the B1, B3 frame. Okay, and we're gonna draw the vector. So let me draw that nicely. I got some weird paint stuff on here. I used acrylic paints. Okay, so looking at the B1, B3 plane, There's B1. There's B3. We've got the angular velocity and the angular momentum. And what is, so this distance from the B3 axis is omega naught. This projection along the B3 axis is omega s. And we can take the, we can look at this angle. We'll call this angle, let me use black. This angle we'll call theta. The angle between the angular velocity, the angular momentum vector and the B3 axis. So cosine theta is that unit vector. So what's the unit vector? It's that vector h divided by the magnitude of that vector h dotted with B3. And well, we know what that is because we've actually got, check it out, we've got all the components of h here. So we can write this out. This is going to be j omega s, right? And then, right, that's the third component here. Now divide it by the magnitude, I naught squared omega naught squared plus j squared omega s squared. How do I get that? Well, take this thing squared times this thing squared, and you get, because it's sine and cosine, you get just I naught squared omega naught squared. All right. So that's what we get. And I want you to notice something about this. This right-hand side here, this right-hand side, it is independent of time. So that means, so the angle theta is a constant throughout the motion. So here's a symmetric rigid body. It's the angular velocity, angular momentum vector. That angular momentum vector is going to always make the same angle with that B3 direction. It'll be theta. No matter how the body is turning, that angle is going to stay the same. What do we also know? We know because this is torque-free motion, the angular velocity isn't changing in inertial space. It's always pointing in the same direction in inertial space. So no matter how this body is moving around, it has an angular velocity that is constant in inertial space. So even though it's in a different direction as viewed in the body fixed frame, it's constant in inertial space. So this is a constant direction in the inertial frame. So we may as well, we have a choice in how to define the three directions of our, here's a different color, the three directions of our inertial frame. We'll choose the third direction to be along that angular momentum vector. So we'll call that E3, right? So we'll define E3, and then E1 and E2 are just two other vectors that fill out the right-handed coordinate system. So this is the third unit vector of the I frame. May as well pick it to be along some convenient direction. All right. now what? We want to, since we want to describe how the body is moving with respect to the inertial frame, that means how is the body frame, this blue frame, moving with respect to the inertial frame, the red frame. We'll use Euler angles. And the one that's convenient for this is the 3, 2, 3 Euler angles. So we'll use the 3, 2, 3 Euler angles. Right, these are also, sometimes they're just called orientation angles. We're using the 3, 2, 3 convention to find the motion in inertial space, or describe the motion in the inertial frame. With the third direction, this is E3 hat, already defined as along the angular momentum. Okay. If you remember, so the 3, 2, 3, those angles, we'll call them psi, theta, and phi. And it's no coincidence that I chose theta. So this theta really is this theta here. It's the second Euler angle for this 3, 2, 3 sequence. If you want a reminder of what the 3, 2, 3 Euler angle sequence is, I think I've got it here, the video. This is a 3, 2, 3 Euler angle sequence. So 3, we do a first rotation about the common z direction, and then an angle theta about the number 2 direction, and then a final rotation phi about the new number 3 direction. So theta, what did we have from up here? This right-hand side is independent of time in this expression. So because that right-hand side is independent, that means that theta is a constant of motion. It's a constant throughout the motion. And that also means that theta dot is 0. So that's a pretty, that's pretty nice. Now, what if we go to the kinematic equations of rotation for these angles? And that's equation 1048. I think we worked these out at least for the 3, 2, 1 Euler angles. The book does it for the 3, 2, 3 as well. And remember, that was the relationship between the angular velocity components and the time rates of change of the Euler angles. Well, we already have this one. That Euler angle doesn't change in time, but we want to know how the other two change. So this is omega 1, and what was omega 1? We got to look back up there. Omega 1 is negative omega naught cosine omega n t. And at least according to the kinematic equations of rotation, omega 1 equals negative psi dot sine theta cosine phi. That's from the kinematic equations of rotation. Omega 2 is omega naught sine omega nt. And according to the kinematic equations of rotation, omega 2 equals positive psi dot sine theta sine phi. What about omega 3? Well, omega 3 is just equal to a constant, omega s, but according to the kinematic equations of rotation, it is equal to b dot plus psi dot cosine theta. Okay, so This will be important to remember, these two. In fact, I'll give them a name like equation square. I don't have to use numbers. I can use symbols. Okay, what next? Well, let's take these two boxed equations. I'm going to square them and add them. And if I do that, I get that omega, no, I want to use a different color. I get that omega naught squared equals psi squared sine squared theta because of some trig identities. I've got that, but theta is equal to a constant. So if theta is equal to a constant, omega naught was an initial condition, that's equal to a constant. That means that psi dot squared is a constant. And what is it? So psi dot equals, it's plus or minus, we don't yet know, omega naught over sine theta, okay? We've got this. We'll see later that it's the positive root. So I'm just going to go ahead and say, okay, it's the positive root. So this means psi as a function of time, right? We already know what theta as a function of time is. It's just whatever it was initially. But psi as a function of time is equal to this constant times time plus whatever psi was initially. We'll call that psi naught. And now what? Now we're going to use the rotation matrix that relates the two frames to write B3 in terms of the I frame, right? This is the I frame. So in terms of E1, E2, and E3. So B3, and we'll write it this way. So the B3 direction, the body fixed third direction here as a function of time. How can that be written in terms of E3, E2, and E1? So the inertial directions. And just based on this rotation, we could look up what the rotation matrix is for the 3, 2, 3 Euler Angles. And then remember, that's what related the B frame and then the B unit vectors and the E unit vectors. So we could write B3 is equal to cosine psi as a function of time, sine theta E1 plus sine psi as a function of time, sine theta E2 plus cosine theta E3. Which describes what? Well, B3 dotted with E3 would be cosine theta, which is a constant. So if I've got, let me draw the E3 direction. And then we've got B3. The projection with E3 is constant. And then we've got sine theta and then cosine and sine of psi, which is changing linearly in time. What this means is that the B3 direction is describing a cone around the E3 direction. So B3, it traces out a cone around E3. And remember what E3 is. E3 is along the angular momentum, a fixed inertial direction in space. So we've got, it traces out a cone with a precession rate psi dot. So there is, think of there being some direction in inertial space given by the angular momentum. And the B3 direction of the body, here's our B3 direction of the body, this one, it's tracing out a cone with this constant rate, the precession rate. So we could sketch that out. You know, here's like a B3 direction tracing out a cone. We call this the space cone. So it traces out a cone, the space cone. Now, what if we want to find phi dot? So we know how two of the Euler angles evolve. Theta is constant and phi changes linearly in time. So I mean psi dot is constant. What about phi? To find phi dot, and hopefully phi, let's write the angular momentum. We'll write it this way. It's the magnitude of the angular momentum, so the scalar hg in the E3 direction. And now we'll write E3 in terms of B1, B2, and B3 using the rotation matrix. So this is what we're going to do. We're going to write E3 in terms of B1, B2, B3. So what is this? We get negative hg sine theta cosine phi B1 plus hg sine theta sine phi B2 plus hg cosine theta B3. And we also know, according to that equation up above, that this is equal to I naught omega 1 in the B1 direction plus I naught omega 2 in the B2 direction plus J omega 3 in the B3 direction. So let's just take the second component. I naught omega 2 equals hg sine theta sine phi. We're just equating components. And this equals I naught, because we have another way to write omega 2, right? We can also write omega 2 using this second kinematic equation of rotation. There's a lot of moving parts here, no pun intended. So we'll write this as I naught psi dot sine theta sine phi. But what do you know? We got sine phis, sine thetas canceling out. So hg equals I naught psi dot. So psi dot, this is just justifying why psi dot was positive. This is hg over I naught, which is greater than 0. So that justified this choice up here of the positive root. And that'll be important because it determines what direction precession will be when we try to bring this all together and interpret it at the end. So psi dot, the precession rate is always positive. And now what? Now we can solve for phi dot from the third of the kinematic equations of rotation, which was that omega s is phi dot plus psi dot cosine theta. You know, everything over here is constant, and we know how to write the expression for it. So phi dot is I naught minus j over I naught times omega s. So this is the rate of the angular velocity coning around B3. Maybe we call it the spin rate. Because the other one was the precession rate. This is the spin rate of the angular velocity. I don't know if coning is a verb. Coning around B3. Okay. If you couldn't follow all of that, maybe, you know, look at it again and the steps will make sense. But now we're going to interpret things. Maybe that will help. We're going to just consider, I want you to consider two cases. What are the main two cases? If J, the angular momentum about the, let me just draw it here. What are the two cases? Is I naught greater than J, or 2, this is a 1, this is a 2, is I naught less than J. Okay, so let's consider these two cases. Suppose I naught is greater than J. So that determines, right? Look at this part of the equation. If I naught is greater than J, then that means that phi dot is positive. And what does this mean physically? If I naught is greater than J, remember J is the moment of inertia about that third direction. So if the moment of inertia about that third direction is the smallest, that means you've got a shape that looks like it's kind of tall and skinny. It's called a prolate body. Prolate. So we've got, well, I've got a tube, so I'll just draw a tube. So this means it's tall, skinny. Technically, the term is prolate body. So J is the minimum axis, J. And there's no intermediate axis. So the other two are the maximum axis. All right. So what does the situation look like? We can look at this in terms of cones. Let me insert a cone. Yeah. So here's the sketch. It's pretty good. I like it. Of what's going on. We've got the, remember I mentioned this body cone. So about the body, there's some cone. That body cone is rolling around a space cone. So we've got that B3 direction. That B3 direction is making a cone around the angular velocity. Let's say the angular momentum. Let's say the angular momentum is the Z direction here. So I've got this thing. The B direction is actually going around that, but there's more to it. We've got the, let me use the same colors as last time. So we've got the angular velocity, angular momentum. I keep getting those two mixed up. The angular momentum, and that defines this E3 direction. It's a direction fixed in the inertial frame, so fixed in space. And then we've got the angular velocity, and that angular velocity is moving around, following the right-hand rule. It's moving around, seen from the top, it's moving around counterclockwise around that E3 direction fixed in space, the angular momentum direction. That is the precession rate. Okay, so this is going around with the precession. And then in addition to that, there's this other rotation that we might call the spin. So we've got a spin rate, which is also greater than 0. Okay, so that's what this will do in free space. If I got it spinning, it's going to do some behavior like that. So let's see a video. Not that video. Here it is. Remember, it doesn't have to be a cone. It just has to be a shape that has the two moments of inertia equal. And then the third one is the smallest moment of inertia. So in this purple thing here is the E3 direction. It's the angular momentum. We've got in blue the angular velocity coning around. So we've got these, it's like two cones rolling around each other, the space cone and the body cone. And together it makes this type of motion. So you have precession and spinning. You see here, in this case, the spinning is a lot faster. Spinning of that body about its I1 axis here is a lot faster than the slower precession rate. So the other case, this was all this had to do with is I1 greater than J or is I1 less than J? If I1 is less than J, then that changes the sign of phi dot and some other things. So that's the other case. So let's now suppose I naught is less than J. This implies that phi dot is less than 0. And we've got something that's flat, short and squished, like a plate or a frisbee or a box or a coin or pancake. All right, so J is now, here's J. J is the major axis or maximum axis, and then we have the other two, which are smaller. So this is a case of something that is short, squished. Well, technically it's called an oblate body. So what did I say? A coin or you know, frisbee. Or a box, a square box that's just small. In the situation here, we could also draw the space cone and the body cone. So let's do that. And here it is. Here we've got one cone inside of the other, but it's not hard for us. And still, you could view the interpretation as you have one cone that is rolling without slipping about the other cone. So think of, we've got the space cone, and then the body cone is this larger cone that's rolling without slipping. These look like the type of cones that dogs have on their heads, like the cone of shame. Our dog has not had to wear the cone of shame, so that's good. Here's the angular momentum, right? And that defines this. It's the angular momentum is the only thing that distinguishes a direction in space compared to anything else. So we'll use that as the E3 direction. And the same thing where this intersection of the two cones is along the angular velocity direction. And the angular velocity is moving around in a cone, tracing out this space cone. But the overall motion of the body is it's rotating about its B3 direction in this body cone about the space cone. The we still have the precession is positive, but then the spinning is that way. So let's take a look at a video of this. Again, so this is a box where these two directions in the kind of plane of the box are smaller than the angular or moment of inertia about that perpendicular direction. So this is the motion. We've got h. The angular momentum is a constant direction. And you see the angular velocity is going around that in a cone. But then what is the body doing? It's got this precession and spin. I think it's harder to interpret the oblate body's rotation. The other one with something as tall and skinny is easier. But that's just me. Okay. So this should at least help you do a couple of the homework problems. You have to do, you actually knew enough from last time to do problem 1. And now you've got enough to do most of problem 2 or problem 3, the one of tossing a coin into the air. There is, so we've looked at this kind of specialized case of when the two moments of inertia, are equal. So there's no intermediate axis. You don't have to worry about that. And you get this nice interpretation of cones. But you really have to try to make something that has two moments of inertia equal. So the more general motion is all moments of inertia are different. So there's a question about what are these cones? Is there a way to see the different cones independently? I think I have a demo. I don't have it ready today, but I could show it next time. That makes it better to see the two cones. It's a Mathematica or Wolfram demo. I just can't get it to work on the iPad, so I'll have to get it to work on the computer. But you don't actually need the cone interpretation to do those homework problems, but it does help with the understanding. So I will try to get that. All right. So the next topic, because this is going to come in when we talk about energy-based ways to get equations of motion. You need to know how to write the kinetic energy of a rigid body, and we haven't discussed that. There's the kinetic energy of a rigid body. And this is gets introduced in section 9.5 of that book, but then it's also in chapter 11. And why do we need this? We're going to need this. It becomes useful for when we analyze free rigid body motion in general. So for the case of all the axes or all the moments of inertia are unequal, and then it becomes useful for another method for getting equations of motion. So this is the method of Lagrangian, the Lagrangian formulation. It's a way of writing the equations of motion just based on the kinetic energy. And we could also use it to analyze something, analyze some other situations. So it helps for, analyzing some motions, just using energy considerations. And I might get to that today. It's something called the caber toss, which is part of the Highland Games. And they're probably not doing it this year, but at Radford, there's this Highland Festival. And one of the highlights is people carrying extremely heavy logs, like trees, giant poles, and then trying to flip them over. And you could do some kind of energetics about, based on the initial flip, will this thing fall over? Like, I don't know what you're talking about. It doesn't matter right now. All right, so we're going to use the same kind of notation we used before. We were writing kinetic energies left and right before. You're like, what happened to all that? Oh, it's coming back. Don't worry. So here is a arbitrary rigid body. Here's its center of mass. Well, let's give it a velocity here. Here's the velocity of the center of mass with respect to the inertial origin. And this also has a some angular velocity, which we always draw as some vector, but we usually interpret it as, oh, this is related to spinning or something. Okay, so we've got, if you wanted to write the kinetic energy with respect to the inertial origin, this would be the kinetic energy of how the center of mass is moving with respect to the inertial origin, plus the kinetic energy of how the whole body is moving with respect to its center of mass. And last, when we were introducing rigid bodies, I think we even said this part is due to the translational motion. And then this part that's due to all the motion relative to the center of mass. Once you've restricted to a rigid body, so you can't have things squishing or deforming, the only possible motion is rotation. So this is now rotational. This is the rotational motion. So we've got the translational motion, kinetic energy, and rotational motion, kinetic energy. And what are the expressions for these? Well, for TGO, the translational motion is, it's like you treat this like a giant particle. So this has mass mg. So it's 1/2 mv squared, 1/2 m, the magnitude of the velocity squared. That's a g with respect to the O, okay? So it's the motion, it's the kinetic energy due to translational motion. All right, if this thing is moving through space, free rigid body, right? It's still, the center of mass might be moving, and if it is, then it's got some kinetic energy due to that translational motion, in addition to kinetic energy of the rotation. So we've got this. if you're following along in the book, that's at page 510. All right, now what about the rotational kinetic energy? Well, it might be useful here to think again of this being made up of a bunch of particles. So here's particle I. Here's the location of particle I with respect to the center of mass. And it's got some velocity. And this velocity can't be just anything. The velocity is intricately connected to the angular velocity. So this is the angular velocity vector cross this location from the center of mass, RIG. Okay, so I'm going to write here this rotational kinetic energy as if this was a bunch of particles. So it'd be 1/2, and then I've got a sum, mass mi times that velocity, but I'm just going to substitute in omega cross r. So this is omega cross r squared. Okay. So this is for a rigid body. Oops. And then we can write this using some identities. And if you want to, you could read all about it. But we write this as omega dotted with the moment of inertia matrix times the angular velocity. Or we could also write this as 1/2 the angular velocity dotted with the angular momentum. And notice we could do that too for the translational kinetic energy. This looks like 1/2 the velocity dotted with the momentum, since the linear momentum is just equal to the mass of the rigid body. I gotta put mg here. The mass of the rigid body times its inertial velocity. P equals mv. So it's got the same kind of structure, so that's kind of interesting. But usually we write the kinetic energy of rotation in terms of just angular velocity and the 3×3 moment of inertia matrix. So I'm just giving you different expressions here. So you could write it this way. It's the angular velocity. You take the transpose. Right, and this is the the moment of inertia matrix. And then this is the angular velocity as a column vector. So this is the one that you'll see the most. You might go, well, which of these is correct? Well, they're all correct, okay? So just different ways to write the same thing. This is the column vector. This is a 3×3 matrix. And this holds even if you're not in the principal axis frame. This is for any frame. This is it's that same thing, but you take the transpose, so you write it as a row vector. So this is the main version used, if you want. I don't know if there's any other name for it. It's the matrix version. And it is, if you're following along in the book, page 511. We could also write the the kinetic energy with respect to the inertial origin. We could do this. We could say that this is 1/2 the angular velocity times, but now it's the moment of inertia with respect to the inertial origin, O. Right, we could take this expression and write it just completely in terms of like it's all rotation, even though we know it's not. I go, that doesn't seem right. No, it doesn't seem right, but we can do it. So this is where the moment of inertia about the point O is related to the moment of inertia about the center of mass via the 3D parallel axis theorem. So you could write it either way. And just as a note, for planar rigid bodies, the rotation about the center of mass, right? This is just 1/2 IG. It's not a 3×3 matrix, it's just a scalar, times the scalar angular velocity. And usually we write that as theta dot. So this is just 1/2 IG theta dot squared. But that's just for planar rigid bodies. Now, in 3D again, if you used a point Q, let's say we used a point Q which is arbitrary, it's not inertially fixed, it's possibly moving around and doing things. So if you use reference point Q, we usually reserve the notation Q for something that's not inertially fixed but could be moving. If you use a point Q, which could be accelerating, well, you're free to do that. Then what do we get? You get a different expression for the kinetic energy. You'd still want to write the kinetic energy with respect to a reference point O. Maybe I'll sketch the situation, so follow along. And the point Q doesn't even have to be on the body. It could just be some kind of, I don't know, maybe it's a moving spaceship. That's V of Q, the inertial velocity of Q. And then you've got our arbitrary body with its center of mass and whatnot. You do need to know where is the point Q. I'll do that in orange. Where is the point Q? This is our Q with respect to G. So that shows up. So you get the expression here, TO equals the kinetic energy of Q with respect to O. So it's as if your mass was at the point Q, even though it's not, plus the kinetic energy about the point Q. But then there's some other term, it has no name, but it's good to be aware of. It's M times the inertial velocity of Q dotted with the angular velocity cross R, Q, G. So maybe just to include that there is an angular velocity here of a body fixed frame with respect to the inertial frame. So you pick up this weird new term that has no name. It's part of the whole bookkeeping procedure because you've used a point Q that could be accelerating. So if this isn't accelerating, something will go away here. Okay. let's just call this our new weird term. So this would only come up if it just turns out you want to use some moving point q, or accelerating. If it's moving, but moving with constant velocity, that's also an inertial point, so that's fine. Okay. I guess to complete this for the arbitrary point, where tq is, we've got 1/2 the angular velocity transpose IQ, where you would use, well, you get IQ however you want. Use the parallel axis theorem. And then that. So that's the kinetic energy of rotation. Okay. Again, this is a lot. You haven't used it yet, but you will want to bookmark this for when we get to Lagrange mechanics. I introduce it here because we needed to analyze arbitrary free rigid body motion. There's another application, and maybe we'll do that in the last few minutes, which is this this caber toss. If you have not seen the I think caber is just like an old-fashioned word for giant log. See which of these. Oh, I think this is a good one. So here's a guy wearing a kilt, Scottish thing, and you see all these people gathered for the games. Listen to that. He's running. He tosses it. It has enough kinetic energy to go over. Hey, can't you just listen to that music all day? All right. So as an application, we'll analyze the caber toss. It's a C-A-B-E-R toss. So what's the situation here? We're not gonna deal with the part where the person's running. It's after they've tossed it and this thing plants into the ground. It has some angular velocity at that point. So imagine it's been thrown from right to left. We've got the point where it plants initially. And this thing has these are, I think there's some standard length. Like you could treat the caber as a rigid rod, a slender rigid rod with a length L. So this is L. It's something like 6 meters. I think they have it at exactly 5.94 meters. And the mass is 80 kilograms. So what's that, over 160, 170 pounds? These are not easy to lift. The people who do it are pretty buff. So this, we'll say it plants into the ground at some initial angle. And we're going to track what that angle does. So the initial angle is theta dot with respect to the vertical. And the initial angular velocity, we'll call that omega naught. Okay. So it's, heading this way, and we'll just write what's the angular velocity squared. It's theta dot squared. So let's just call this, it's theta dot naught. Where's the center of mass? The center of mass is halfway up the rigid body. So we got G, so that's actually L over 2. What's the height above the ground? It's H. What's the inertial velocity of this? It's so this has some kind of inertial velocity, G with respect to O. If we use an energy approach, well, first, what's our question? The question is, for a given initial angle, for a given initial angle, what initial angular velocity is needed for a successful toss? A successful toss means that it can just barely make it over the vertical position and then it falls over. Or a successful, I guess we could call it flipping of the caber. And we will use an energy approach. So how will we do that? The potential energy, we're going to do a balance of total energy. There's the potential energy, and it's just due to gravity acting on the center of mass. So that is capital U is mg, and then it's h, the height, which is mg. What is h in terms of geometric things, and L and theta? So it's L over 2 times cosine theta. Okay, that's what h is. The kinetic energy, we can write it two different ways. And this kind of illustrates something from above. If we call this point here, this planting point is the point O, we could use the pivot point O as our reference. And if we do that, so it's TO, then we could just treat it as it's pure rotation about the point O. So the kinetic energy of rotation about O. And so we could write that as 1/2 the angular moment of inertia for a rigid rod about the point O. And so let me just write up here, what is the moment of inertia of a rigid rod of mass m and length L about its end? If you haven't memorized this, it's 1/3 ml squared. Okay, so we have 1/2 I naught omega squared. So this is 1/2 1/3 ml squared theta dot squared. Okay. We could also use, the center of mass as the reference, which means we're still writing kinetic energy with respect to that point O. Kinetic energy is the kinetic energy due to translational motion of the center of mass plus the rotation of the body about its center of mass. So yeah, this is translation of G, kinetic energy. And this is rotation about G. So you would write 1/2 m, the magnitude of the inertial velocity of the center of mass squared, plus 1/2 ig, and then it's the same angular velocity squared, so omega squared. What is this? You could work out what this is, because we know where the center of mass is. We know what theta dot is. So this ends up being L over 2 theta dot squared. What is the moment of inertia for a rigid rod about its middle? It's 1/12 ml squared. And that's something that you either have calculated it once or you look it up. So we have this 1/2 m plus 1/2 1/12 ml squared theta dot squared. And this ends up being the same thing. So good, it's the same. And now we'll assume that the total energy is conserved. So that means E equals T0 plus U is constant throughout the portion of the motion that we're studying. So if we were to write the expression now, just adding these two, the kinetic plus the potential, we'll get 1/6 ml squared theta dot squared plus mg L over 2 cosine theta. And we'll say, what is this initially? Initially, we're at 1/6 ml squared omega naught squared plus mg L over 2 cosine theta naught. And we want to know, so when theta gets to, go up here, when theta gets to 0, we want there to be just enough energy to go over. And so that's at 0, and theta dot is just barely above 0, but we'll just substitute in 0. So energy 0, 0. This is just mgl over 2. So we could set this equal to what it is initially, and then we could solve for omega naught. So we've got this, and yeah, so for example, if the initial angle, it looks like it's often about 30 degrees, then we need that the angular velocity is greater than square root g over L 3/1 minus cosine theta, which is about 0.8 radians per second, or if you want 46 degrees per second. So if you start with some angle, right, 30 degrees, then this has to be moving at 46 degrees per second to be able to barely make it to the top with just enough energy that it then goes over. And then you've won the caber toss.